Today we're here to talk about what is a rainbow. But before we get to a rainbow, we have to get to what is light. So, let's actually find out what light is. So let's start by saying that light is a wave that travels through space. An electromagnetic wave, as a matter of fact. And of that whole electromagnetic wave that travels through space, only one tiny part of that wave is the light that we see. That tiny part of light is the size of a pinhead, a sewing pinhead. On the smallest size of that entire wave, who wants a drop of water in their hands? One drop of water, oops, for you, one drop for you, one for you, you. I just put a drop of water in several people's hands. In that drop of water, we have atoms that make up everything. That one drop of water has 100 sextillion, 365 quintillion atoms in that drop of water. That's a lot, and a lot of empty space in a way. Just to give you a perspective, this number here I've underlined, 7 billion would be a number that you put there. That's the number of people on the entire planet Earth. That's how many atoms are in a drop of water. The smallest part of this electromagnetic wave is even smaller than that. On the large end of the wave, Mount Everest. It is the height of Mount Everest, which is as tall as 11 of the tallest buildings in the world, or 2 Pikes Peaks from the ground, from sea level, I should say, up. That's pretty big. So light is a wave, and it travels through space. An electromagnetic wave, and light is one part of that wave. So, settled, done, no more discussion, right? Light is a wave. But no. Light is also a particle traveling through space. A single ball of energy, you might say. Well, how is that possible? How can light be both a wave and a particle? Lights, please. Let's let someone with a vaguely Scottish accent explain it for you.
Light isn't really like anything we're used to dealing with in our everyday lives. Is it a particle, like atoms? Or is it a wave, like ripples on the surface of a pond? Sometimes it behaves like a particle, and other times it behaves like a wave, but it isn't exactly like either. For one thing, 2 beams of light that cross paths don't interact with each other at all. If light were made of tiny solid balls, then you would expect that some of the particles from beam A would crash into some of the particles from beam B. If that happened, the 2 particles involved in the collision would bounce off in random directions. But that doesn't happen. So it's settled then. Light is a wave, right? Not so fast. In the 20th century, scientists did experiments that appeared to show light acting like a particle. For instance, when you shine light on a metal, the light transfers its energy to the atoms in the metal in discrete packets, called quanta. This results that light sometimes behaves like a particle, and sometimes behaves like a wave, led to a revolutionary new physics theory called quantum mechanics.
Quantum mechanics. That's why you can be, lights on please, 2 things at the same time. May I have you stand up, please, and come over here? How good do you think you can make this thing move like a wave across the room? Go up and down, and then walk. Okay, stay right here. Just a moment, please. You. I want you to stand. Lock that way. I want you to stand right behind him. Can you grab those 2 pieces of metal and pinch when I tell you to? So, there you go. Hold it like that. So light is both a particle and a wave, and walk. Both of you hold on. Keep walking. Go back. Go back. Give me some waves. Give me some waves. There you go. That's what I'm talking about. Light is a particle and a wave. Now, before we explain how this is possible, thank you both very much, we're going to do a little experiment. An experiment. I need a volunteer, please, to come up here. Me. All the me's in the room, you please. Glasses, yes. Don't worry, I will try to give everyone a chance, but life is essentially unfair, and I will not be able to do all of you, but I will try my best, okay? So what I'm going to ask you to do, can you come up here? Oh, okay. Can you hold this flashlight and aim it roughly at the wall there when you turn out the lights? Give or take, okay? Everyone tell me, I have a pencil here. What is going to happen when I take this pencil and put it in front of that light? It'll what, please? It'll make a pencil. In what way will it make a pencil? Will I suddenly have two pencils?
It'll make a shadow.
It'll make a shadow of a pencil. Let's see. By golly, you're right. I get one. Stay there, please. What if I do two pencils?
It'll make two pencils in a shadow.
Let's see. By golly, you're right again. All right, turn on the lights, please. Just one small set will do, the back lights. All right. So, when you shine a light, you may sit down, sweetheart. Thank you so much for your help today. Shine a light, you put an object in front of it, you cast a shadow because the light hits the pencil, the particles, bloop, 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 but other particles go around and go straight to the wall, and you have a shadow. Well, that seems pretty straightforward, doesn't it? Nothing more to talk about there. That's all I have to say about that. What about if I take pencil lead? Anyone know what pencil lead is? What is it? It's exactly what it says it is. It's the lead inside your pencil, but it's the lead by itself. You use them in mechanical pencils. Yes? That is correct. It's what rubs off on the paper to draw. I have to take my glasses off for this because I can't see close up without it, and you guys are going to have to give me some help. I'm going to shine a light on that back wall. What's going to happen when I put this pencil lead in front of the light? What are we going to see? Shadow, okay? Let me know if you see anything different or give me guidance until you do. Okay. Is something happening? It's getting wider. Good, it is happening. What is, why I'm not getting a shadow. I'm getting a strange thing instead of a shadow. Am I getting the pattern up there now? Good. I'm getting a pattern, a radiant pattern. Let's see what that means.
Here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing.
That's what you saw
when we throw
with a pencil lead.
That is matter through two slits, we get this, two bands of Higgs. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marble, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How do pieces of matter create an interference pattern like a wave?
What you see there is the interference pattern that you saw when I took the green pointer and shined it on the pencil lead. Light is sometimes a particle and sometimes a wave, and that's how you can demonstrate it to anybody, including your Aunt Millie if she happens to be around. And you have to blame all that weirdness and not being one thing or another only on quantum physics. So, where does light come from in the first place? Yes, we have bulbs and all of that, but what is the primary ultimate source of light and energy on Earth? Yes? The sun, exactly. This light that comes to us, and it's not just light, because light is one small part of the entire electromagnetic wave that's coming to us, gives us heat and light. This heat and light comes from a reaction, a nuclear reaction of two gases, helium and hydrogen. I need a volunteer, please. Someone who's not done something yet, please. You, please. I'd like you to come up here, please. Turn around and face your audience. I'm going to put this chair right behind you. You stay right there. In general, gases are a pretty complex thing to explain. But there are some ways you can explain what a gas is quite easily. Would you please have a seat? Have a seat. That is what a gas is. Would you like to try that again, or are you done? Give it a good one. There we go. Now we have gas. Excellent job. Thank you so much for illustrating what a gas is. These two gases, helium and hydrogen, are in an atomic reaction, creating an atomic explosion. The sun, to put out all that light and energy, is having 9 trillion atomic explosions every second. How many people here have ever seen on a movie or anywhere an atomic explosion? Raise your hand, please. Yeah, not many. I grew up during the Cold War. And believe me, this stuff was on TV and in books and everywhere all the time. Let's take a look, lights out please, at just what an atomic explosion is. Just one of the 900 trillion a second. That was a baby explosion. Lights on, please. That was a baby explosion, around 50 kilotons, 50 to 60. The sun is more on the scale of 5 to 700 kiloton explosion, 9 trillion of them a second. That's a lot of heat and a lot of energy, and that's why it can come all the way to us. Speaking of which, just as a fun fact, 1,300,000 Earths would fit comfortably, happily in the sun. The light travels to us 93 million miles, traveling at a speed in a vacuum of 186,000 miles a second. That is a lot. But what does that mean to us? It means the sun is so far away that it takes light 8 minutes and 20 seconds to get to us. Who in here has a timer on their phone or some other way they can get to really quickly from the grown-ups? You do? Get your timer, set it for 8 minutes, 20 seconds, and let me know when you're able to start. An electromagnetic wave giving all the primary heat, light, and energy to the Earth 93 million miles away. 8 minutes, 20 seconds. Mark this point in time in the calendar of your life because it will be impressed in your minds forever. Or maybe just for a few minutes. Go. 8 minutes, 20 seconds to get to us. While it's on its way to us and after it gets here, light behaves in 3 different ways. First, it travels in straight lines. It also reflects up. And it also refracts out and in. 3 things light does all the time, all the ways. Let's talk about straight lines. How do you know for sure that lights travel in straight lines? I need 6 volunteers, please, who haven't done anything yet. Let's see here. All roughly the same size would be good. You, and you. Each of you come up here. 5 of you stand just like I'm standing on a square. 1, 2, 3, 4, 5. And I need 1 person, like you, please, to come over here. And I'd like you to stand on this square facing that direction. Just like that, okay? Everybody stand up straight, please. I want to see your rough heights. Okay. Everyone's going to have something to do in this group. Please take a spray bottle. 1, 2, 3, 4, 5. Please hold this, but don't do anything with it yet. Okay? And whatever you do, do not point it in your eye. All right? So, everyone, raise arms, present. There you go. Safety's off. Remove your caps. Can you get the caps off? Pull. You have to pull them off. 1, 1, 1. Whoops, that's the whole thing. Just want the cap off. Not yet. You'll have your turn, I promise. All right, I want you all to practice spraying your bottles. Please point away from yourselves and show me how much spraying you can do. Fast as you can. All right, excellent, but not at your friend. All right, so, good. We are almost ready. I'm going to hold this line as I go across. I want you to be sure that your sprayer is held up at the same height as this line. Oh, you're a little open there. Here we go. Be sure your sprayer is held up at this line, facing out. So hold up your sprayer so it's right at this line. Hold up your, that's fine. Your sprayer right at this line. Don't spray, just hold it up. Don't spray, just hold it up. All right. Now, you, my good man, your job, we're going to take this pointer. The button is here. Turn straight this way. You're going to turn it on, and when they start spraying, hold on please, you're going to be aiming your light through their spray. All right, but not yet, when I tell you. Okie dokie. All right, lights off, please. Now, begin spraying. See if you can spray towards the beam. So now you have proof that light travels in a straight line. Turn on the lights, please. Please cease fire. Cease fire. Please put on your safeties. And then please deposit all of the sprayers right here on the table, and you can all sit down. Thank you so much. Everyone give a hand for our group. Thank you. So light does travel in a straight line, one of its characteristics. Light also does something called reflection. And it really has two kinds of reflection. The first one you're all pretty common with, is called specular reflection. Light comes in and bounces off at a nice, even angle, making a reflective surface. Specular reflection, a nice, clear image of the world, and it bounces cleanly. Second, on a rough surface, it's called diffuse reflection. Following the spectrum, it's really hard to see. You don't see a clear image. So we have examples of specular reflection, really nice, you can see yourself, and diffuse, you look kind of fuzzy, if at all. But we're going to talk about, in terms of learning about what is a rainbow, just specular reflection, or nice and easy bouncing. Flat mirrors. Have any of you done the kind of cool trick where you take two mirrors and put them together, or four mirrors together? When you stack your mirrors, you get a nice, beautiful little image of yourself. Well, a flat mirror is a flat mirror is a flat mirror, and it's kind of flat and boring. But what about if you can bend a mirror? Something called a concave mirror. Concave mirrors, if you take a mirror and you bend it inwards like a cave, you create a really interesting reflection. Whoops, sorry, keep skipping ahead. The concave mirror. Light comes in, whoop, 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 and then gets bent and angled out. It's reflected, not bent, sorry, reflected. And then something really interesting happens. It twists. And look here at this reflection. Let's take a moment to look at this in terms of something called a Hobson's box. It's a box for doing light and optics experiments. Lights off, please. I have in my hand a concave mirror. It's bent inwards. Watch what happens when I take this concave mirror and bring it up to the lights. What do you notice about the red and the green? They're shooting out, but what are they shooting out in the same places they went in? They have done what? They are switching in different directions. Exactly. And you can see, let me see if I can get it right here. Right in the middle, about here, you can see the focal point where they come in and they do the switcheroo. A tiny spot. Lights on, please. You see concave mirrors every day, though you may not think about it, because every car headlight is a concave mirror. And there are lots of other examples, too. Now, I'm going to pass another mirror around, just like the other one, but you guys can practice making concave mirrors. Hold it a certain distance from your face, and you should notice something interesting. Tell me, I just handed it to her, please. Bend the mirror. What do you notice about your face? Are you right side up? You are. Instead of right side up, you are upside down. But are you upside down in this room? To me, you look right side up. Pure as I can see daylight. There you go. Pass that around, please. That's what's happening with a concave mirror. Light coming in, being angled back out as it's reflected, and then doing a nice little twist. It's what's called a focal point. Guess what, everyone? When I told you a while ago to remember that moment in your life, that's how long it took that sunlight to get to us. Two things to be interested about there. 8 minutes, 20 seconds is also the time you have from the moment the sun explodes until you know about it. Just a friendly warning. Well, there's also something called a convex mirror. Light comes in and then gets reflected out, but at an outward angle. Let's take a look at that. Lights off, please. Now I'm going to use the convex side of my mirror. It bows out, it bends outward. When I put it in front of the light is now reflected outward from its source. Is it flopped? Is it switched? Is red still where red was when it went in? Is green still where green was when it went in? Yes, it doesn't flip-flop like the concave, but it bends outward. Lights on, please. It doesn't, reflects outward. It reflects. And you see an example of this probably every day in a school bus mirror. It reflects, it brings in and essentially more light and reflects it out. And you can take your same piece of mirror and instead of bending it in, for what kind of mirror is this when I bend it in? Concave. I'm going to make it a convex. So again, light coming in and being reflected out at an angle. This is really fun to look at together. You can see here on these little stripes coming in, what kind of mirror is that? On the right side, the words are right there. Convex. The lights move inward. The lines move inward and converge. Here the lines move and diverge or move outward. A funny little thing, a very complex thing that you will never ever see in your everyday life unless you eat cereal. Because when you get a spoon, my spoon beware. Look at it one way, the side you eat from, you have what kind of mirror? The side you eat from goes inward, so it's a cave. A cave goes inward. The other side that your tongue goes on, convex, exactly. So now we've talked about reflection, and we talked about straight lines. Now we're talking about refraction. Light being moved outward or inward as it passes through something. Mirrors reflect, lenses bend light. Well, one way to see this in live action format is to do the pencil and water experiment. Has anyone here done the pencil and water experiment? No? All right, you, please come up here, please. Okay, look at your audience. Oh, my daughter has the exact same one. She loves it. I would like you with the hand that's not cuddling to hold up this glass to the group right in front of your face so you can see it too. And am I holding up a perfectly nice straight pencil? Does it look straight and nice to you? Yeah, pretty straight. Zippo, zappo, alakabam! What do you see now when you look through the glass? It is getting bigger, and it is, but what else is happening? Look at the straight line of that pencil. It looks like it is taking the pencil apart, like the pencil is broken. But indeed, it is not. Will you take that, sit down, and pass it around the room, please? No one drink out of it. You have no idea what might have happened from another class. So in your everyday life, you drop a pencil in water, like you would do that in your everyday life, and you see how a lens, in this case, the water and the glass, are bending light. Something I want to be clear about here before we go on is that what's happening is not reflection. We've already talked about reflection. That was mirrors. We are talking about transmission. The light is transmitted. In these balls, light is transmitted rather than reflected. Concave lenses work different than concave mirrors. I have here a concave lens. Let's see what happens when I expose it to the Hobson box. the light spreads out. It refracts. It's no longer in a straight line. Are the colors switched? Is red coming out the opposite side or the same side? Yeah, what about green? Exactly. The only difference is the light is spreading apart. Lights on, please. You see this right here. They diverge out like that. What about a convex lens? This lens bends outward. Let's turn the lights off, please. Now look at the light waves. What do you notice happening as the red comes out of the lens? It's twisted, isn't it? It's on the other side. I'm sorry. It is a straight line, but the yellow continues to be straight. How very fascinating. But the other two switch at the focal point. Convex lens. So all of this is something beautiful in this wonderful math called Snells Law. Snells Law, all of you memorize it because no one will be allowed to leave this room until they solve for this equation. Yes? No? Okay. The practical application of Snell's Law can be simply seen in what we're doing here with the water. Light is being, I'm just putting quotes around it right now, bent as it passes through a medium, in this case, water. When I look at a pencil in the air, you don't notice anything about it. But when it passes through the medium of water, when the light passes through the medium of water, something changes. What does this mean? Light isn't really being bent. It's being slowed down. A volunteer, please. Who hasn't done anything? You, please. I'd like you to stand right here. I would like you to face where I am over here. And I want you to walk to me as fast as you can. I said walk, not run, but okay. All right, excellent. Nicely done. Now go back. Now I want you to pretend you are in a pool of water up to your neck. And try to do the same thing and make it happen just as it would happen if the water was up to your neck. Very good. You're traveling faster or slower than in the air? Excellent. Thank you. Have a seat. You're traveling slower because you've changed mediums. You've changed what you're traveling through. Light is affected the same way. When light comes through the air, it's traveling a little less than 186,000 miles a second, because in a vacuum, there's nothing to stop it. What's a vacuum? And I don't mean, what is it? Well, maybe I kind of do. What's a vacuum? Anyone? It is a void. Take a vacuum, actually, you know what? Let's see if I have something here that will work. I need a grown-up. Any grown-ups will volunteer? Come on up, please. Thank you. Tell me if this cup will fit snugly over your mouth to make a good seal. Does it? Mostly? All right, now try to suck all the air out of that. See that? She is creating a vacuum in that cup, a lack of air. And because there's air pressure built on the outside, it's pushing it in. She's not so much sucking the air out as she's creating a vacuum, and the air is pushing it in from the outside. Thank you very much. So, light is coming in at its speed traveling through air, and bam, hits water and slows down. Light is affected by what it travels through. What's the upshot of this? Let's take a look at this cat hunting a fish. This cat is looking in the water, but because light is being, what? Slowed down. it actually looks to this cat like the fish is way up here, even though the fish is actually down here. For the fish who wants to avoid the cat, looking up, the fish sees the cat as higher than it is when it's actually here. So they're both in trouble unless they know how to adjust for light traveling through a medium. So, quiz time. What is going on here? Stare at it intently for a few seconds. Stare for a few seconds. I'll let you go first. We've talked about lots of things. This is a review of everything we've talked about. Your hand was up first. What do you see happening here? Excellent. The cup is on this side a concave mirror. What then is it on this side? Yes, there are two surfaces, and it's not really a mirror, it's a lens. But it's acting like a concave lens on one side and a convex lens on the other. Top marks, top marks. Yes, you. Where's it reflecting, please? Where do you see a reflection here, please? This side of the table or this side? Right side? That side? I will offer to you that, remember I said the difference between transmission and reflection? Those little clear balls are transmission, things go through. Reflection were the silver balls where it bounced back. So which one is the reflection here? One right here, because the light is being reflected back. This is transmission, because the light is going through. Clear things, light goes through. Mirrors, light bounces back. Excellent. So we have concave, convex, transmission. Anyone have anything else? Yes. In fact, most of what's going on here in terms of the water, the medium, that's Snell's Law. But then we have the lenses going on as well. And those are the lenses are basically the glass. One side concave, one side convex. So what we have here is we have transmission, light moving through. We have reflection, light coming back. We have refraction, because we're moving through a medium. And we have concave and convex lenses. And who knew there was so much physics happening in one glass of water? But there it is in your everyday life. What is color? Color is the response produced when light strikes an object and then comes back and is in your eye. Let me let someone, again, with a vaguely Scottish accent, tell it to you better. Lights off, please.
One of the most striking properties about light is that it has color. To understand the phenomenon of color, it helps to think about light as a wave. If light is a wave, then it must have a frequency, right? Well, yes it does, and it turns out that we already have a name for the frequency of the light that our eyes detect. It's called color. That's right, color is nothing more than a measure of how quickly the light waves are waving. If our eyes were quick enough, we might be able to observe this periodic motion directly. But the frequency of the light we see is so high, it waves up and down over 400 million times a second, that we can't possibly see it as a wave. But we can tell, by looking at its color, what its frequency is. The lowest frequency light that we can see is red, and the highest frequency is purple. In between, all the other frequencies form a continuous band of color called the visible spectrum. So, what if you had a yellow pencil sitting on your desk? Well, the sun emits all colors of light, so light of all colors is hitting your pencil. The pencil looks yellow because it reflects yellow light more than it reflects the other colors. What happens to the blue, purple, and red light? They get absorbed, and the energy they're carrying is turned into heat. It's similar with objects of other colors. Blue things reflect blue light, red things reflect red light, and so on. White objects reflect all colors of light, while black things do exactly the opposite, and absorb at all frequencies. This, by the way, is why it's uncomfortable to wear your favorite Metallica t-shirt on a sunny day. The idea is that very few objects actually emit their own light. The special, light-emitting objects, like the sun or a light bulb, are known as sources of light. Most of the things we see, like that pencil on your desk, are simply reflecting light from the source, rather than producing their own. So, when you look at your pencil, the light that hits your eye actually originated at the sun and has traveled millions of miles across empty space before bouncing off the pencil and into your eye. Which is pretty cool when you think about it.
8 minutes, 20 seconds outdoors for the light to get to you, and then all of it goes into this pencil, and only the yellow comes back to your eyes. Pretty cool that there's so much going on that you take for granted when you see. Something also that we might take for granted is how this little process happens. We talked about it already. When light goes through a certain kind of medium, what happens to it? If it's a thicker medium than a vacuum, faster or slower? Faster. When you're in a pool versus when you're walking, air walking is faster or slower than a pool? Air walking is faster or slower than a pool? Faster. Exactly. The medium is water. In this case, the medium is a prism. Lights out, please. If I take this prism and I hold it just right for this incoming white light, you will see a rainbow. Because the white light, as it passes through the rainbow, through the prism, which is a medium, it's slowing down the different colors of light and breaking them apart so you can see them. Because each one travels at a different speed, is one way to think of it, or frequency. That's why you are able to see a rainbow. Not sure if I can get it from every side. There you go, there's another one. Lights on, please. So, when you look at an object, what's coming back at you is the color that is reflected off of that object. You look at a plant, all the colors are coming in, but green is bouncing back. All the colors are going in here for the flower, but red is coming back. White light, everything is being reflected back. Black, everything is going in. And what did the video say happened when all light goes into a dark surface? It comes back as what? Not light, but have you ever gotten into a car in the middle of summer, has black paint and black interior? What has happened when you've done that? Hot, 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 hot! Way hotter than a white car with a light interior. Because all of that energy from the sun is now being absorbed by that black. When I was a kid, school buses were the same color as yours. They were yellow. Some things never change. But one thing did. My school bus was all yellow everywhere except for the black lines. What about school buses you see now? Say that again, please, louder. They have black trim on the outside, but I'm talking about the outside of the school bus. Is it yellow all over? No, what does it have? Look on the top of a school bus. What color is it now? Not black. Well, it is black up in the far, far north, where it's really cold. But here, where it's more temperate, what color is it? White, because white does what? Reflect all that light. So it doesn't have as much heat, and it keeps the darn thing cooler. That happened in the last, 300 years since I was in school, somewhere. God, it feels like it. Types of color. Everyone knows that when you mix paints, you get certain results, like yellow and blue make green. Very good. Red and blue make purple. But that is not true when it comes to light, because light is a different system. Light is what's called additive color. When you add colors, you get something different in a different way. When you mix colors, you may think of it, I'm adding colors together, but you're actually subtracting light that's reflected. You're subtracting reflected light in a pigment. You're adding light when you mix light. Lights off, please. So let's take a look at this for a moment. This is a list of color mixtures. Look at the yellow color down here. What does that say that you mix to get yellow? Again, reflected light. What two colors do you mix to get yellow? Blue. Blue here is being absorbed. It's not reflected. What two colors are being reflected? Red and green. Let's see if that really works. I'm going to add red, and from the side, I'm going to slowly bring in some green. You can see it coming, and I get yellow. It's a kind of yellow because my lens is imperfect. My machine is not the best, but that is a shade of yellow. If I start out covering this, I give you green first, and then I add in the red, you get yellow. Lights on, please. What about when we mix up lights? What do we mean that white is made up of red, green, and blue light? Well, that doesn't quite make a whole lot of sense. Lights out again, please. I'm going to start with some red light. I'm going to slowly add green light. And again, remember my machine's a little imperfect. Red and green make yellow, but when I add blue, and again, remember this is imperfect, but it's close. Come on, blue. I'm going to bring blue in from the side here. We get white light and the spectrum around it. And again, it's close enough to white because the board isn't a perfect white and these aren't perfect reflectors. Lights on, please. So I'm going to take this, I'm going to skip a level here and go to what does filtering do? Filtering, what happens when you filter water? What are you doing? Anyone? Use a water filter? Yes. What happens when you filter water? That is the water cycle, very much so. But I'm thinking more of like when you have water that's kind of not so good, but you want to make it good, you do what with it? To get the junk out of it, you filter it. I used to live in Flint. I know a lot about filtering. Okay? I only wish the administration did. So, filtering means removing something from light, removing a color. What color is this? Red. Lights out, please. What color do you see here mostly on this screen? You see some, but what do you see most of? Okay, good. Fair. You got me on that one. Besides blue and white, what color do you mostly see? Red. Let's see what happens when I filter red out of the light. You see a secret message, don't you? What does it say? No, it doesn't, because I'm not filtering it anymore. Lights on, please. Yes, if you filter out the red light, that works. So how does all of this make a rainbow? Well, scientifically speaking, a rainbow is a meteorological phenomenon. No, that doesn't mean things that strike the earth. It means weather. It's caused by the reflection, we talked about reflection through surfaces, and refraction, moving through mediums, clear things, of water droplets. In short, what we have is the sun coming in, white light, hitting a water droplet, and the colors coming back out, slowed down and broken up, but it's way more cool than that. Watch this, folks. We're going to pull it all together here. You ready? White light comes in. It hits the water droplet, the single drop of water I started with earlier with the 9 gazillion atoms in it. It hits a lens, which is a convex lens, and refracts. It's also in a medium that slows it down and separates the colors. It bounces off the back. It reflects on a concave lens, which we know twists light, and then it passes through another lens, which is now a concave lens here, and is emitted as a rainbow. And that's how you get there, folks. I'd like to close by saying that as a child, I came from a very underprivileged family. I didn't even know there was a library until I was 10 years old. My family never exposed me to this kind of stuff. I worked very hard to gain an education in my life, and I work very hard now to use that education to care for my children full-time, a 5-year-old and an 8-year-old, and to bring opportunities like this to you. Anyway, I appreciate your attention, your time, and best of luck to all of you. Take care. Goodbye.